Welcome to PyData Global 2021. My name is Dea and I will be your host for this session. Our presenter is Markus Löning. He is one of the core developers of sktime, a unified Python framework for ML with time series. He recently finished his PhD at UCL, and now he's working as a data scientist. During his PhD, he spent 9 months at the Alan Turing Institute. His research focuses on ML, time series, and analysis and software design.
Okay, thank you, Dea, for the introduction. And welcome, everyone. This is the sktime tutorial. I'm very glad to be here, and I'm really looking forward to the next 90 minutes. Yes, so this is to set the expectations. This is a beginner-friendly tutorial, so we assume some familiarity with the common PyData stack, including pandas and scikit-learn and NumPy, but not much more beyond that. So you don't need any previous experience of working with time series. We also like to make this as interactive as possible. This is sometimes a bit hard on Zoom, but we encourage you to ask questions, chat with us, run the notebooks locally or on Binder. I will share the link in the chat so that you can just play around with the code and get to know us a little bit and you know, find out more about sktime and how to use it. And in order to facilitate this, we have 4 helpers from the sktime community in the chat. So that should be, there should be plenty of people to give you answers in case you get stuck, or to ask for more info in case I skip over things. Okay, so for today, the plan is as follows. We first want to give you an intro to machine learning with time series. And to some extent, that will be a summary of the tutorial from last year. So if you want to learn more about this, I think it makes sense to go back to this. And in particular, you will learn about the different learning problems that you encounter when you work with time series. You will learn about algorithms that can help you solve these learning problems and different ways how you can build machine learning models. And that includes both specialized time series algorithms, but also ways how you can reuse scikit-learn to solve these problems. And then while the tutorial is focused on users, there will be lots of comments on software design decisions that we've taken and how you can, as a user, extend sktime so that you can implement your own algorithms, which you may need for your projects. And I should also say that this is not an introduction to algorithms, but more of an intro to a software framework. So we will show you how you can use different algorithms within sktime and how you can combine them with other packages. But we will not say a lot about how these different algorithms work internally. And we will have 2 smaller breaks in between to give you a chance to ask questions, of course, but also to move around a bit. And finally, before we get started, sktime is still a relatively young toolbox. We started a bit over 2 years ago now, I think. So some features are still experimental and they still need to be consolidated. And especially over the year, we've made great progress. So it's slowly maturing, but there's still lots of work that needs to be done. And that makes it even more important for you to give us feedback and to tell us if anything is missing, that you know, any feature that you'd really like to see, or if things are not working. Okay, so I'm going to switch over to the notebooks now. So can you still see my screen? Can you see the GitHub repository?
Yes.
Okay, great. Okay. So this is the GitHub repository that we're going to be using today. The link was just posted in the chat, and you can find the notebooks in the notebooks folder. So there are three notebooks and one Python file for utility functionality. And then you can also find the link to Binder. So if you want to run these notebooks in the cloud without having to install anything, you can just click on this link and it will open a Binder notebook for you. Now I'm running these locally, and I've opened the first notebook here. So the one intro, and yes, so before we dive into machine learning with time series, I think it makes sense to start with scikit-learn, because I assume that this is what everyone will be familiar with. And if you're unfamiliar with scikit-learn, they have really good documentation, so you can check out their Getting Started guide. As an example data set, we look at the diabetes data, and we here have, so we can load this in, and we see our feature data, and it's a data frame, and each row here represents a different patient, and each column represents a different kind of measurement that we have from the patients. And in addition, we have a target variable, which is y, that we would like to predict from the variables that we have here. And of course, we can plot this. So here I plot two variables. On the y-axis, you have our target variable that we want to predict. In this case, it's the disease progression. And on the x-axis, we plot one of the measurements, namely a blood serum measurement, this column. And the typical workflow for this is that you specify a model, you then fit the model. Once you have a fitted model, you can generate a prediction. And once you have a prediction, you'd like to evaluate the prediction so that you have an idea of how well the model would perform in the real world, in the actual deployment situation that you're trying to solve. So in scikit-learn, we do this as follows. Well, first of all, before specifying the model, we split our data into training and testing sets. And then we specify our model, and this happens on this line. And I think this will be familiar to most of you. So additionally, if we want to, we could set a number of hyperparameters for the algorithms. Here, I just use the default. And then once I have a fitted model, I can call fit. Once I have a specified model, I can call fit on it, pass the training data, so both my features and my target data, and that will change the state of this object. So it goes from a specified model to a fitted model. And once that happened, I can call predict using the predict method and pass the additional test data that's needed for generating predictions. And then once I have a prediction, I can compare it against my test set and look at some validation metric. Now, of course, scikit-learn offers much more than this. It offers modular model building, so you can build much more complex models with a few lines of code. For example, you can do pipelining, tuning, ensembling, and yeah, you can compose more complex models from simple components. So in this case, we first standardize the data and then fit the different algorithms, and we put this together. We chain these two operations together in a pipeline. And the nice thing is that the pipeline now is a model itself. So it takes in models, but it's also a model itself. It still has the fit method with the same input parameters and the predict method with the same input parameters. Oh, I need to import it first. Yes, so this is what scikit-learn does in a nutshell, in a very brief summary. And I want to highlight a few points. So first of all, scikit-learn mostly deals with cross-sectional data. So when we look at the data here, there isn't really a temporal dimension in this data. the data wasn't collected over time, and instead the main dimensions are different kinds of measurements and independent observations, so from patients in this case. Another thing I'd like to highlight is that scikit-learn, it mainly covers 3 learning tasks, and that's cross-sectional classification, regression, and clustering. And the example above here was regression, and the classification and clustering interface is similar. And for each of these learning tasks, scikit-learn provides a common API for the estimator. And this is what essentially fit and predict is, together with a few other interface points. And these APIs, when you look at the signatures of these methods, so what are the input parameters and so on, they closely mirror the learning task that you're trying to solve. So when you look at the fit method, for example, X here will take in cross-sectional data, and Y is a vector of the target series. And this is this mirrors directly the learning task, namely the cross-sectional regression that we want to solve. And you will see the same for classification, where the target vector, instead of consisting of continuous values, it consists of categories. Okay, so much for scikit-learn. And now what we try to do with sktime is to take this to the time series domain and to generalize this and to extend it so that we can handle different time series problems. And as said, I will skip over this relatively quickly. But if you want more examples of how these data formats are different in the time series domain and what the different learning tasks are, you can check out the tutorial from the PyData Amsterdam from last year. So when you deal with time series, you have multiple data formats. The simplest format is that you just observe a single time series. And that consists of repeated observations over time from a single variable or kind of measurement. So instead of observing data from multiple patients, we observe a single kind of measurement here from a single time series. And we can here plot the number of links trappings, for example, over time. This would represent such a univariate time series. Of course, in many situations, we observe multiple time series at the same time. And this can happen in 2 ways. So the first way is what we call multivariate data. So here you have repeated observations over time from multiple related variables or kinds of measurements. So for example, here I load a macroeconomic data set and I can plot this. And this shows me some economic measurements like the gross national product and the total employment. And we measure them over the same time horizon. And of course, they're closely related. But we can also observe multiple time series in a different way, namely by observing repeated observations on multiple independent experimental units. And what I mean by this is, for example, the patient data that we had above, but instead of observing single measurements in time, we now observe for each patient a time series of measurements. And here in this example, I show you what this would look like. Each line in this plot represents the data from a different sample, from a different independent sample that we have. This is what we call panel data. So with these different data formats, there are different learning tasks or learning problems that you may encounter. For example, forecasting. So you may want to predict the future values of one of these time series. You may want to classify these time series. So for each time series that you observe, you assign a single category or label to it. You may want to annotate time series. So you may want to assign a label or some annotation to each time point of a time series. Or you may want to cluster time series. So you want to identify and group together similar time series. This is just a selection of learning tasks. There are many more. But what's interesting about these tasks is that while they are all distinct learning tasks, they're also closely related. And I hope that this becomes clear in this diagram. So what scikit-learn covers is, in terms of at least the supervised learning approaches, is tabular regression and tabular classification. Tabular here meaning cross-sectional. What we try to do with sktime is to cover a number of time series learning tasks. And we will discuss, today, we will discuss forecasting, classical forecasting, time series classification, and a little bit of time series regression. And what we will highlight is that once you have an algorithm for one of these problems, you can still use it in many cases to solve another related problem. For example, if you have a time series classification problem, you can still use a scikit-learn classifier to solve it if you do certain adaptations of the problem. Similarly, if you have a classical forecasting problem that you want to solve, you can still use, by following the kind of like the arrows on the top, you can still use a regression algorithm provided by scikit-learn, but you need to be careful to adapt the problem in the right way. Now, this reduction here from classical forecasting to tabular regression, just to give you one example of what this looks like, is shown here in the diagram, and I will later show this in code as well. So we take a single time series and we cut it up into different segments by using a sliding window. We then stack them on top of each other. And this tabularization gives us the required input format for the scikit-learn regressor. And we can then put this data into the scikit-learn regressor, which is the little robot inside the bigger robot. And then once we have this regression model, we can use it to generate forecasts. So this is one way of still using scikit-learn to solve the time series problems. And in sktime, we provide dedicated functionality to make it easy for you to do these, to use these approaches. Okay, before we dive into the code, I want to quickly give you an overview of what we're trying to achieve with sktime.
Markus?
Yeah.
Yes, I don't know if you want to put all the or answer all the questions together, because there is a question that is not being answered. I don't know if you want to be answering as.
Oh, I didn't see this. We can. I think the helpers can take questions.
Yeah, that's the idea.
So there's one. I'm seeing one. Is that correct? There's only one.
I only see one. Yes, but I wanted to know.
Okay.
So, thank you.
No, thank you. Thank you for letting us know. Yes, so a quick kind of like outlook of, or our vision, what we're trying to achieve with sktime. So we're trying to cover multiple learning tasks, and similar to scikit-learn, we're trying to provide a common estimator API for each of these learning tasks. And then, like in sklearn, each of these APIs, as we will see, mirrors the learning problem. So in terms of the fit and predict functions and how they are, what input parameters they require. In addition, we like to, improve the existing ecosystem of packages. What you will find is that there are many very cool packages out there, but it's still very hard, I think, to make them work together, to use them in the same workflow. And what we try to achieve with sktime is to make the ecosystem more interoperable and more usable as a whole. And we do this by providing a common API and then by interfacing existing packages so that people can use stats models, for example, or fbprophet or PMD ARIMA from within sktime. Yes, I think I've mentioned this. So a lot of the work that happens in sktime is this framework development, and you will see shortly what this looks like. There's also research on algorithm development happening. So if you're interested in that, please feel free to reach out to. And of course, we're building and growing an open source community with of people of different backgrounds in academia and industry. And we're giving tutorials like this one today. Now, one aspect I want to highlight is this idea of a framework, and we will come back to this. So the way I understand the framework is that we try to try to develop different design templates. And by design template, I, for example, mean a code skeleton of what a forecasting algorithm or what a classification algorithm should look like. So what methods does it need to have in terms of fit and predict? What input parameters do they take? And we hope that by developing this framework, it becomes easier to use and compare different algorithms, and also for you to extend the existing framework to implement your own algorithms. Okay, so that was the introduction. I will now jump into the code. And I've opened the second notebook on forecasting. And we will cover 3 cases of forecasting. Univariate, this is the simplest case, and then univariate with exogenous variables and multivariate forecasting. One quick question, is this readable? I should have asked this at the beginning. Should I make the text bigger, or can everyone read this well?
It's readable.
Okay, perfect. Yes, okay. So in forecasting, what we want to do is we observe a certain time series in the past, and at a given point in time, we want to make a prediction about the future values. So in a way, we want to make a temporal forward prediction. And the basic workflow, so we will discuss 2 workflows. The basic one, where we generate a single prediction at a single point in time. And then later we will discuss a more advanced workflow where we want to generate predictions repeatedly and as time moves along. So let's start with the basic workflow. And the workflow is very similar to what we've seen in scikit-learn. We first need to specify some data. We need to specify the learning task. So what exactly do we want to predict? We need to specify the model, and then we need to fit the model and generate predictions and evaluate the predictions. So some example data for time series looks like this. So this is the number of shampoo sales during the 90s. So it's a single time series, multiple data points. And we're interested in predicting future values of this. Now, in terms of the task specification, we know the target series that we want to predict, but what we still need to predict, to specify, is what exact points in the future do we want to predict? And this is what's called the forecasting horizon. So in this case, we will try to predict the last 6 months of data. So this is monthly data, and this is not entirely correct. So this is monthly data. So we will hold out the last 6 points of test data, and we use a 6-step ahead forecasting horizon. So at a given point in time, we want to predict the next 6 steps ahead. Yes, and then we use some evaluation metrics in order to quantify how well we're forecasting. Now in sktime, there are different ways to specify this forecasting horizon. And we try to make this as convenient as possible for users. When you look at the ecosystem of packages, you will find that each package has its own way of specifying the forecasting horizon. So what we try to do in sktime is to make this as convenient so that you can use many different ways and work together with different packages. So very simple ways, you just use an array of a numpy array of values. So if I run this, this could be my forecasting horizon. It just says I want to, predict the first step, the second step, third step, and so on. Or we have a forecasting horizon class in sktime, and you can also use that to specify your forecasting horizon. So in this case, I'm saying that I want to predict, these absolute time points in the future. And I specify this is relative false here, because in this case, I use absolute time points that I want to predict in comparison to the relative time points here. So these are always relative to the last point in my training data, whereas these ones are absolute time points. I can convert between the two. So if I have an absolute forecasting horizon like this one, I can convert it to a relative one at any given cutoff point. So at the end of the training set, this is the last data point I have in the training set. So if I run this, it will give me exactly the same relative forecasting horizon as specified here. And once we've done this, we can do a train test split, and we can use the forecasting horizon to do that split. And we can plot the data. So this will now be our test set, and this will be our training set. Having done this, we can specify a model, and this is the same as in scikit-learn. So we instantiate the model, we pass any parameters that we would like into it. In this case, it takes a strategy, and we use a drift strategy, and we can specify the window length as well. Once we have specified the model, we can then pass the training data to give us a fitted model. And now this is, since this is forecasting, the fit method is slightly different to what you're familiar from scikit-learn. So note that the first argument is the target series that we want to predict, because this always has to be present in forecasting. And then optionally, we can pass exogenous data, and we will discuss this below. And if you like, you can already pass the forecasting horizon in fitting. In this case, we don't do this, but some models will require the forecasting horizon already in fitting. So we make it optional whether to pass it in fit or in predict. So once you have the fitted model, you can call predict, and the predict signature takes in the forecasting horizon and exogenous data and a few other parameters. Now this is a naive strategy, so it just predicts a linear trend, but you can see what this prediction looks like in comparison to the test data. And then similar to what we do with scikit-learn is you can then compare the prediction against the test data that we have, and that allows you, it gives you some idea of how well this model would perform when you deploy it. Just to give you another example, so this is exactly the same workflow. The only thing that changed is this line, where instead of using a naive forecaster, I now use auto-reamer, and I specify some additional parameters, and it gives me the prediction from auto-reamer. So it's really easy to try out different models with the same workflow. The only thing that you have to change is the specification of the model. So in summary, this is the basic workflow. So we use a single fixed cutoff point. We generate only a single prediction, and sktime provides a common interface for forecasting tasks with dedicated fit and predict methods. I just noticed that there's a sound problem. Is that still the case? Or can everyone hear me still?
I can hear you very well.
Yeah, you're good.
Okay. All right, perfect. Okay. Yeah, so that's the basic workflow. And we've seen two example forecasters that you can use, the naive one and the auto-reamer. Now, if you want to find out what other estimators we have in sktime, there are two ways. One is you can go to our website, and in the documentation, you will see an estimator overview. And this table gives you all of the estimators that we have in sktime. And if you like, you can also filter it by forecasting, for example. And this will give you all of the forecasting algorithms that we have in sktime, as well as the authors that created these. So if you have questions, it will be easy to find out who to speak to. The other way is to do it in code. So we have a registry module, which collects all of the estimators that we have. And from this, you can import a helper function or estimators. And you can run this, and you can specify that you're only interested in forecasters. So you can specify the estimator types that you're interested in. And then you will get a list of the estimators and where you can find them in sktime. So it becomes easy for you to find them and to import them. Now,
Can I maybe add the very quick thing? So
sure.
you can also filter by tags, and there's all the all_tags function. So for instance, if you want only multivariate forecaster, you can use all_tags to print a list of the tags. And then you look up the tag, for instance, that tells you what does it mean multivariate, and you filter by that.
Yes, I'll discuss this a bit later when we talk about multivariate forecasting. But yes, you can filter by estimators and tags. We'll come back to this.
Yep. Okay. Sorry for interrupting then.
No problem. So at this point, you may wonder why you cannot just use scikit-learn. And this is something we've addressed in the tutorial from last year. So the answer is, in principle, yes, you can use scikit-learn. But if you do it naively, there are many pitfalls, so many dangers that you have to carefully maneuver around in order to make sure that your data science workflow is still solid and robust. So as a better solution, we suggest to use scikit-learn with sktime. And this brings us back to the robot diagram, which we've seen in the introduction. So if you want to use the scikit-learn regressor to solve a forecasting problem, we provide dedicated functionality for this. And this will take care of all of the additional data transformations and the application of the fitted regressor automatically. So you don't have to worry about this. And what's nice about this is that it makes the use of scikit-learn for forecasting very modular and easy for you. It also makes it parametric and tunable. So in this transformation, there are certain parameters like the window length. When I apply the sliding window here to chop up my time series into equal blocks, the window length is a hyperparameter that I as a user have to specify. If I do this naively, it may be very hard to tune this. So with sktime, it becomes easily tunable. And the nice thing is, once you've done this, if you use sktime, the regressor itself, if you wrap it in an sktime class, behaves as if it were a forecaster. So you can still easily compare it to other forecasting algorithms without having to write any extra code. So let me show you how this is done in sktime. So here we just load another time series. So this gives you the number of airline passengers. Again, it's monthly data, and we've collected this data over the years. We do the same thing again. We split our data and specify a forecasting horizon. In this case, we're interested in predicting the last 12 months, so the next year ahead. And now let's assume that we want to use k-nearest neighbors from scikit-learn. In order to use that, we first specify the scikit-learn model. This is what we do in this line. And we can use any hyperparameters that we like. And then we use the helper function from sktime. And what this function does is it returns a forecaster that internally uses the regressor. And you can specify how you want that to happen. So this encapsulates, this forecaster here encapsulates or is, is represented by this diagram. So inside we have the regressor, and the outside robot is the forecaster itself. And you can specify different parameters of how you want to do this. So if we run this, so you have different options for the exact strategy. And that includes a direct strategy, recursive strategy, or multi-output strategies. And you can read up on them. We provide a link to a nice paper that explains what they mean. And you can specify the window length of how many, when you do the sliding window operation, how long should that window be? Yes, so with these parameters specified, we then get a forecaster. And as said, the forecaster has exactly the same interface as any of the other forecasters in sktime. So it becomes really easy to train and predict them. So in this case, we pass the data again. And since we passed the forecasting horizon here already in fit, we don't need to pass in predict. The model will remember it and generate a prediction for you. And this is what the prediction looks like. So it's the k nearest neighbors prediction using the recursive strategy. And do this becomes a forecaster. Okay, so this is the basic workflow for a single cutoff point. And I'd now like to look at the more advanced workflow that you may encounter in real-world applications. And the advanced workflow is as follows. So again, we specify the data, the task, and the model that we want to use. We then, again, fit and predict the model on the training data. But once we have generated the first prediction, in practice, we often observe new data coming in as time moves on. And as time progresses, we want to generate a new prediction and at the same time make use of the latest data that we have. So we observe new data, then we want to update our existing model using that new data. And once we have the updated model, we want to generate a new prediction. So we repeat the steps 5 to 7 as time progresses. So let's see how this works in sktime. We start off by, again, loading some data and then specifying the task that we want to predict. So in this case, we are interested still in predicting the next year, the 12 steps ahead. And then we need to select our training data. And here we say that our training data consists of the data up to August 1957. So somewhere here. And this is at this point in time, that will also be all of the data that we've observed. And so here I just print out the tail. So this is, the last re-observation that we've made. Once we have this data, we then specify a model. In this case, I use the auto ETS model. And then I fit the model on the training data. So this is, so far it's the same as the basic workflow. And then once I have a fitted model, I want to generate the first prediction. And this is what it looks like. So at this point in time, so let's look at the prediction values actually. Yeah, so the notes here aren't correct. So at the time, at August in 57, we now predicted the next year ahead up to August 58. Okay, and now in a live process, we would then observe the next data point. So we're in August 57, and we then observe September 57. And this is what we simulate here. So our observed data is now goes up to September 57. And our new data point is exactly that observation for September 57. Now, what we can then do with this in sktime is we have our fitted model, and we can then pass the new data point to the fitted model, and that will update the model. Now, in this case, you get a warning, and there are different ways of how this updating can work. Now, very simple strategy is to just refit the entire model based on all of the observed data that you have. But in some cases, there are more efficient algorithms that instead of refitting the entire model, they use the fitted model and then some specific updating algorithm to update the parameters without refitting the model as a whole. Once we have updated the model, we can then generate a new prediction, still for the same forecasting horizon. And you will see that this still gives us a prediction for the next 12 months, but it has now moved up by 1 month. So the first month that we predict here is October, whereas previously the first month was September. Yes, I've printed the doc string for update here, and it, as said, it's the fallback option is to refit the model as a whole. You could also use this update method to just generate forecasts for new cutoff points. So as time moves on, you always want to predict the next 12 months. But perhaps you don't want to update the fitted parameters of your model actually. Perhaps you're happy with the fitted parameters from your initial training set. And while you still want to always predict new, make new predictions, you want to do this without updating. So you can do this by setting the update params parameter to false. And you can, of course, also use exogenous data, and we will discuss this below. Now, this was a manual step through the process. So we stepped through it manually, and in sktime, we have lots of functionality to help you automating this so that you can simulate this process during model development and evaluate your models. And in particular, what we have is an evaluate function, and we have window splitters that allow you to split the time series iteratively. So to give you an example, if we want to do this kind of temporal cross-validation, we could use the expanding window splitter. And we say we have a step length of 3. So every new window will be 3 steps ahead. And we have an initial window of 10 time points. And then if we plot the windows, it would look like this. So the first window consists of 10 time points. And then we have our forecasting horizon of 12 time points. And then we step by 3 to get the next window. And since it's an expanding window, we keep all of the previous data points in the window. We have a dedicated notebook for this if you want to find out more about the different window splitters and different ways of doing temporal cross-validation. Now we can use this to evaluate forecasters in this advanced workflow. What we need to do for this is, again, we specify a model. In this case, we're using the naive forecaster again. We then need to specify the way how we want to split the model and the way how we would use it in practice. And we can then pass on all of this information to the evaluate function. And that will do this update predict loop internally automatically. And we can look at the results. So this just shows that the first result, but you will see that those are the metrics from the first window that we had, which we specified to be 72 data points long. And then we had a step length of 12. So for every new window, we add 12 data points, we get the corresponding evaluation metrics. So to visualize this, we could look at it like this. So up to this point, that's our training set. We train our algorithm on that data, we generate the first prediction and compare it against the actual data. We then move 12 steps ahead, update our algorithm with all of the past data, make a prediction for the next 12 steps and compare it against the actual data. And we do this repeatedly. Yes, so that's the more advanced workflow. And what I want to talk about next is the advanced model building and composition functionality in sktime. And as said, these models can be used in either workflow. And I want to talk specifically about tuning and about pipelining. So in tuning, we're interested in optimizing some of the parameters, some of the hyperparameters that we need to specify during model construction. For example, when we use the make reduction helper function, we had to specify the window length. And that may be a parameter that we want to optimize because we may not know what the best parameter is. So we can use temporal cross-validation to find the best parameter from the data that we have. And this is very similar to how scikit-learn does it. So we specify a parameter grid. Here our grid consists of different window length and also of different parameters for the regressor that we use. So the k-nearest neighbor regressor has one of the parameters are the number of neighbors. And we want to tune them simultaneously. Our temporal cross-validation scheme is we want to use a sliding window splitter. And we specify the window length of each window and the same forecasting horizon. Now, with all of that information, we can then pass this to our forecasting grid search CV. And we can then pass the training data and fit and the forecasting horizon and predict. And that will try out all of the different parameter combinations, generate predictions and evaluate them and then pick the best one. So once that's finished running, we can look at what the best parameters are. And in this case, it chooses the number of estimators to be 2 and the window length to be 12.
So maybe a quick question, because I'm also not sure here myself, the window length here, that's the window length in the reduction, not the window length in the sliding window splitter, right?
That's correct. So the sliding window splitter is that specifies the way how we want to evaluate this. Whereas the window length here specifies our model.
So we do nested sliding windows, windows inside windows, right?
Yes, in a way, yes. Yep. One sliding window operation is part of the model itself. That's the reduction operation. And one sliding window operation is part of the evaluation scheme.
Thanks.
And this again, this visualizes the parts of the data in this sliding window scheme. So each window here is, what did we specify? A length of 60, and then we always have the forecasting horizon as the next 12 steps ahead. That was a a simpler tuning example. In some cases, you would like to not just tune the parameters, the hyperparameters of the forecasters that you use, but you would also like to, compare different models themselves. And this is sometimes, what comes under the name of AutoML. And we also have a dedicated functionality for this. So in this example here, what we're interested in is to find out which of these forecasting algorithms is the better one for our prediction task. And we can use this multiplex forecaster to specify the choices of algorithms or the selection of algorithms that we want to compare, and then tune over this grid over that selection. The workflow is the same. We specify the grid search, pass over all of the parameters, and then call fit and predict. And in this case, it selects the exponential smoothing over the naive forecaster. Another way to build more complicated models is pipelining. So in pipelining, you first transform the data, and then you fit the forecaster on the transformed data. And during prediction, you first generate the forecast, and then you inverse transform the forecast so that you come back to the original dimension of the data, the original scale of the data. And in sktime, we can do this as follows. So if we're interested in transforming the target series, we can specify a list of transformers and a final forecaster. So in this case, we first deseasonalize the data. We detrend it, so we remove the linear trend, and then we fit the forecaster on that deseasonalized and detrended data. Once we put everything into a pipeline, that pipeline behaves the same as any other forecaster. So we can just call fit and predict on it. Oh, I need to import it first. Yeah, I'm not showing the prediction again, but the idea is the same. So that was the univariate forecasting scenario. One variation that you often find is that you have additional exogenous data. So you have a single target series, which sometimes also is called endogenous data, and you observe that data only in the past. But in addition, you have one or more related exogenous time series, and you observe them in the past, but also for the period in the future that you're interested in predicting. So in many cases, you may observe some other variable into the future. So that could be calendar information that you can just look up in the calendar, like whether someday in the future will be a public holiday, or it could be some other variable that may be easier to predict than the target variable that you're interested in predicting. So you can use the prediction for the one variable in order to predict the other variable. Okay, let's quickly go through this in the basic workflow. So here we load a data set with exogenous data. So we have a single target series, and we have a number of related time series. And the workflow is the same. We specify a forecasting horizon and split the data, this time both the target series and the exogenous data. And then we specify model, and we pass the exogenous data as our X to the fit method. And then in predict, we need to pass the additional exogenous data that corresponds to the forecasting horizon to generate the prediction. And then for the target series, we get a prediction. And now this uses both the past data of the target series, but also the contemporaneous exogenous data. Pipelining also works with exogenous data. So when I scroll up here, we transformed the target series using this pipeline. But in some cases, we may also want to transform the exogenous data that we have. And for this, we have a forecasting pipeline. So here I'm loading some other macroeconomic data. I'm specifying the forecasting horizon and splitting the data. And then we can specify pipeline. So if there's missing data, we may want to impute the data first. We may want to scale the data using different approaches. And what I use here is an adapter. So I have to wrap it into this class because this transformer here comes directly from scikit-learn. And you can still use any scikit-learn transformer by just wrapping it into this class, and it will work within the forecasting API. And after these transformations, I then use the auto-reamer model. And as before, I can call fit and predict. The only difference is that these transformations will now be applied to the exogenous data rather than to my target series. And you get a prediction out. Okay, so far we've discussed the simplest case univariate forecasting and univariate forecasting with exogenous data. Another forecasting problem is multivariate forecasting. And what we want to do here is we want to predict multiple series at the same time. And this is what Franz mentioned. So if you're using sktime and you want to solve a multivariate forecasting problem, you may wonder what kinds of algorithms can handle this kind of problem. So you want to specify the estimator type to be a forecaster, but you don't want any forecaster because you only need those forecasters that can handle certain types of input data. So what you can do is you can specify the tags. So in sktime, all of the estimators that we have a tag or have multiple tags, and these tags describe them further. So one tag is, for example, the type of the Y data that can be accepted. And this can be univariate, multivariate, or both. And if we're interested in multivariate forecasting, we would set this to multivariate and both. And then again, we get a list of the algorithms in sktime that can handle this kind of data. Now, to show you two examples, we first load in some data, and we split the data. And now what I should show here is that if you look at Y-train, it consists of two time series. And we're interested in predicting both of them at the same time. Now, a very simple approach is you could say, I know that these two time series are related, but I still want to predict both of them separately. So I know they have some relation, and using that relation may be a good idea, but as a baseline, I just want to predict both of them separately. And this is what we call by column or by variable ensembling. And we have a class for this, the column ensemble forecaster. So you can say that for the first column, so the index 0 here, I want to use a polynomial trend forecaster. And for the second column, I want to use exponential smoothing. I pass these forecasters to the ensemble. I pass my now multivariate training data, and it will fit this model on the first column and the exponential smoothing on the second column, and then return the predictions from it. So at this point, I haven't made use of any information that's in having both of the series in their relationship. But it may still be a good starting point. Now, if you want to use more complicated models, you can take a list of the ones that we already have, This is also an active area of development in sktime. So we're working on adding more of these models over time. Now, one common model is the vector autoregressive model. And we use under the hood, we use stats models. But we allow you, if you import it via sktime, it uses stats models under the hood, but it allows you to follow the same workflow as for any of the other models. So you can specify the model. If you like, you can, I need to import it first. If you like, you can specify any of the parameters that you know from stats models, but you have the same interface as for any of the other forecasters in sktime. And you will then get a prediction from the vector autoregressive model in sktime. Yes, and this brings us to the end of the overview of the forecasting functionality. Now, what's really nice about sktime, and this brings us back to the framework idea, is that we provide specific algorithms, so toolbox functionality that you can just import and use directly, but we also provide a design template that you can follow, and if you follow that, all of the code that you write will be compatible with the other functionality in sktime. And the way we do this is we have extension templates. So when you go, I should start here, when you go to the main repository of sktime, you will find a folder called extension templates. And in here, you have the files for the different learning problems that we currently cover. So if you click on the forecasting one, you will find a detailed description of, you know, how a forecaster, how you need to implement it so that it's compatible with all of the other functionality in sktime. And we also provide a code skeleton, so you can just copy the code that you find here and then work through it and change whatever it says to do. And that gives you, you know, the ability, and makes it really easy for you to implement your own algorithm, your custom algorithms, which are still fully compatible with the rest of sktime. Okay, so in summary, we talked about sktime having a unified API for univariate forecasting and multivariate forecasting. I've shown you some examples of how we interface other packages, but expose them through a common API. So we've seen scikit-learn, and we've seen stats models. The auto-rema class that we've used uses PMD-rema under the hood. And I think there are a number of other packages like Prophet, but also tbats and so on. And this is still work in progress. We're still trying to add integrations with other models. We've also seen how you can build complicated or composite models in a modular fashion. So we've seen pipelines, we've seen ensembles, we've seen tuning, and we've seen reduction. And I've quickly shown you, if you want to build your own model, hopefully it's easy to do that. And then at the end here, I list a number of other useful resources, but you will also find them in the previous tutorial. So at this point, I suggest we take a quick break, perhaps 3 minutes, 3 to 5 minutes. If you have any questions, feel free to ask them. And then after the break, we jump into the classification notebook. Okay, it's 43. And I'm going to continue with the classification part. So we have roughly 15 minutes left. So I may skip over some of the things in this notebook, but you can always try to run through it on your own. And then if you have any questions, ask them on the Slack, or on the PyData Slack, or you can get in touch with us on our GitHub repository. We have our own Slack space and a few other communication channels, and you're more than welcome to raise issues there or to get in touch with us. Now, classification is quite a different learning task. So what we're interested in here is we have a training data set where we observe multiple time series, and they come from independent experimental units. And for each of them, we observe some category or some label. So in this case, it's the color. We have one time series with the blue label and two with the red label. And the goal is to train an algorithm which can then predict the label of a new unlabeled series. The workflow, though, is very similar to what we've seen in scikit-learn. So we specify the data, the task. We then specify the model, and then we fit and predict. What we use in this tutorial on this notebook is some time series data set from the UEA repository. And this is I've added the link here. This is a website which has lots of time series classification data sets. And the table for you to look them up, and to, it always has some description on it as well. What we have in sktime is a helper function that allows you to easily download data from the website, and then it stores it locally so that you can make use of that data. So we first load the data, and then for convenience, we convert it to a 3D NumPy array. We have like a common function for this that hopefully makes it easy for you to convert between different data formats. When you have this kind of panel data, there are many different ways of how you can format this. You can use a pandas data frame, you can use NumPy, you can use other ways. And with this function, we try to provide some conversion functionality so that you can easily load the data in whatever format you have it, and then convert it so that you can use it in sktime. So we load our X, our feature data, and our target series here consists of two kinds of labels. So it's a binary, so this should say binary. It's a binary classification problem. Now, what does this data look like? Here I plot two of the time series, one for each label. And this is some data on Italy power demand, and you're trying to predict whether this time series occurred in the summer or in the winter. And here I just show one example for each of the labels. Now, the workflow, I said, is very similar to scikit-learn. We first split the data, and we then specify the model. So in this case, I use Rocket, and you can find out more about what the algorithm does. There's the repository of the original code, but it has also been ported into sktime, like many other algorithms. And there's a nice blog post here that explains you more intuitively what the algorithm does. So we specify the model, and we then fit the data. We fit the algorithm passing the data. Now, when you look at the fit method, it looks almost identical to the scikit-learn method, but there is one key difference. Namely, this X here is it no longer represents cross-sectional data, but it now represents panel data. So what you passed in as the feature data is not a data table as we've seen in the introduction, but it's a data table which has some time index. So you observe for multiple experimental units, you observe something over time. And all of the time series classifiers in sktime, they need that kind of panel data. So there are specialized algorithms to work with panel data. Once we have a fitted classifier, we can pass the test panel data, and we get a prediction out of it. And then, since it's a classification problem, we can use scikit-learn's, classification metrics. Here we look at the accuracy score, and we will see that it predicts 97% of the series in the test set correctly. As before, you can, if you want to find out what classifiers we have in sktime, you can use the estimators function, and that will give you a long list of dedicated time series classifiers. Again, you may ask whether you could not just use scikit-learn. And here the answer is, in principle, yes. But research has shown that using cross-sectional algorithms may not be as powerful as using dedicated time series classification algorithms. And at the bottom of this notebook, I provide some links for different benchmarking experiments. And you can also see more info on this in our previous tutorial from the PyData Amsterdam. But if you still want to use scikit-learn, that's fine, and you can do that with sktime. Now, again, the problem that we're trying to solve is a time series classification problem. So there needs to be some conversion to make it, to adapt it to the classification, to the cross-sectional classification setting in scikit-learn. But we provide functionality for this. So you can use the tabularizer to convert the data from panel data to cross-sectional data. And then, as before, you can use any scikit-learn classifier to solve the problem. And in some cases, it may work well. In other cases, it may not. So in this case, it performs slightly worse than the dedicated time series algorithm. We also have advanced model building functionality for time series classification. So you can do pipelining, ensemble tuning. I've shown you an example of reduction here. And this works very much as it works with scikit-learn. In fact, we use the pipeline class from scikit-learn.
So quick question. I think someone is asking, can you print out xtrain just for showing how it looks like here?
Yes, that's a good question. Let me do this quickly. So as said, there are different ways of representing this kind of data. Here we have it as a three-dimensional NumPy array. So what does this mean? So it means that we have data on, over 1,000 experimental units. So for example, patients. For each of them, we observe one kind of measurement, so one variable. And we observe that variable over time for 24 time points. But as said, there are other ways to represent this data. This is what we call the NumPy 3D representation. I hope this answers the question. Yeah, so we have pipelining, and of course, another way to use scikit-learn is if you have time series data, you first extract features, and then you fit some scikit-learn regressor classifier on it. And here we use the tsfresh feature extractor. So tsfresh is a package which is dedicated, which provides automated feature extraction, and that allows you to easily, extract features and use scikit-learn to solve a time series classification problem. Now, a very closely related learning task is time series regression. The only difference here is that the target series, the target variable does not consist of continuous values. Does not consist of categories, but of continuous values, as with cross-sectional classification and regression. So what I want to show you is that first of all, the workflow is still the same. We can load the data. Here I plot the distribution of the target variable. Here I plot some of the time series of the feature data. And we can still use the same functionality. So here we use part of the Rocker classifier, so just the kind of the time series processing step, and then we use a random forest regressor, and that still works in the same way. But we can also come back to our reduction example, and instead of using a tabular regressor in here, we can use a time series regressor. So we still convert the data, but when you look at the data here, it is, in a way, it is panel data, because we have multiple rows of data, and in each row we have a time series. So we could use a cross-sectional regressor, but we could also use a time series regressor. And to do this, we can use the same function as before, the make reduction function. The only thing that we have to change is we have to specify the site type of the estimator. And in this case, we want to say it's not a tabular regressor, but it's a time series regressor that we're using.
Markus?
Yep.
We only have a few minutes left. I'm sorry.
Yes, I know.
We want to wrap up. Thank you.
Yep. Thanks for letting me know.
Thank you.
So what I wanted to show with this is that this is another relationship between different learning tasks and how we can reuse an algorithm for one problem to solve another one. And the final topic I wanted to talk about was multivariate time series classification. And I've added some notes here. So perhaps this is something we leave for you to play around with in your own time. One last thing that's worth highlighting is that in sktime, we have many of the state-of-the-art time series classification algorithms. So the current state-of-the-art, I think, is an algorithm called Hivecode version 2. And that has been implemented in sktime. So if you want to try this out in practice, it's also really easy for you to try. And as before, we have extension templates. So if you want to build your custom classifier that's fully compatible with the rest of sktime, you can use the template. And at the bottom here, I have a number of additional resources that you may find interesting. For example, the benchmarking and the link to our deep learning package, where we provide deep learning algorithms. Okay, so that was a quick tour of the classification module in sktime. Before we go, I quickly want to give you an outlook of what's on the roadmap. So let's switch back to the presentation. So on the roadmap, the following topics. So we want to add support for time series clustering, and there's already an experimental module. And we will further consolidate this and hopefully provide time series clustering functionality in a robust state sometime soon. Someone asked in the chat already about anomaly and outlier detection, especially in the forecasting setting. And this is also work in progress. There's an open pull request for this, and there's some basic functionality in sktime already. And there's active work on other forecasting tasks like hierarchical forecasting and panel forecasting. And finally, we continue to work with other package maintainers in the ecosystem to work towards a more unified API for solving these different learning problems and for making the ecosystem more interoperable and usable as a whole. Now, the very last thing that I want to show you in the last minutes is our website. If you want to find out more about sktime and if you want to get involved, You can read more about this here. So we have a number of activities happening almost every week. We have a mentoring scheme. So if you're new to contributing to open source or to machine learning with time series, you can apply, and we will try to connect you with one of the more experienced developers so that you can make your first contribution to sktime. And we have a number of meetups that you can find out about here. So we have a calendar of the different activities that are happening. We have weekly collaborative coding sessions. We have different meetups on roadmap planning, and you're welcome to attend any of these. Your feedback as users or developers is always appreciated. And I think we're at the end of the time.
Yes, thank you very much, Markus, and your team. Thank you, everybody who came, and I hope you have enjoyed it. And I'm gonna stop the meeting, the recording and the meeting. Thank you very much. Bye.
Thank you. Bye-bye.
Thank you. Bye.